Yes. We are on YouTube right now.
Good.
There is.
And then the video on YouTube stay in the platform, no?
Yes. After the video will stay in our YouTube channel, then the students that cannot see the webinar right now can see it later.
Yeah. I try to not put a lot of unpublished results in any case.
Yes, it's better.
Yeah.
Let me see. We are almost on time. I will ask you to wait for 4 minutes, more or less, to have all the students in the YouTube. Then we can start.
Okay. So the students are they will follow the presentation in YouTube. So there cannot be any question or
they will follow in the YouTube, but they can send me the questions. I can see the chat from YouTube. Then I transmit to you. Then you can answer.
Okay.
Last year we used to make all the things here in the mconf platform, but sometimes the students have problems with the login, and the internet sometimes was not good enough. Then we changed to YouTube. But then the interaction is not that good.
Yeah, but at least they're following with no problem.
Yes. See, we have 3 people watching. Bom dia, pessoal.
There are so many? How many there are?
Normally, it's around 30 people.
Okay. And all specialized in natural products, or just?
There is a mix of a lot of things. There are people from natural products. There are people from toxicology. There are people from microbiology, pharmaceutical technology.
Go deeper in the details of natural products, because.
Yes, but there are a lot of people that work with natural products, so it's not something completely strange for him.
Okay.
So, let me see. We have 10 people. Bom dia, pessoal. Good morning to everyone. So today we have Professor Sergio Ortiz from Université de Strasbourg. Thank you, Professor Sergio, for has accepted our invitation to be here in this webinar. I think we can start. It's 11 o'clock here. I will turn off my camera and my microphone to not disturb your presentation, but I will be here listening, and if you have any trouble or anything, you can call me, that I am here.
Good. Okay, so good morning all of you, and first I would like to thank for the invitation to present to you today some of the work we are doing here in Strasbourg. We will see all the context and all the project in the big framework, and some very interesting results that I would like to present to you today. So thank you again for the invitation and for the time that consecrated to hear me. First of all, the presentation that I will present today is about the antibacterial antivirulence activity that we are developing and exploring from some natural products, specifically some neolignans isolated from Krameria lappacea. But this presentation, this result, they come from a very big project that I will today to present this project, and then we will go to the specific about this result. Just to be in the context of this project and to understand our principal motivation, just to indicate and as you know, right now the current emergency of one of the principal health problems in the world, the emergency of bacterial resistance to antibiotic, that until now they are causing, and there are some estimations that are causing more than 1 million deaths worldwide after a few years before the COVID-19 pandemic, and is this problem produced principally for the overuse of modern antibiotics are indicate like one of the top 10 global public health threats according to the World Health Organization. So there are a lot of not only in pharmacognosy or natural products chemistry that we will talk today, but in different field of the different scientific field, they are putting all the effort for one point to try to overcome this bacterial resistance, and also try to open our minds and think about new therapeutic strategies to try to fight this resistance and this global threat. So it is in this context where the needs for find new therapeutic options is placed our project about the antivirulence compounds, and how it is indicate how is placed in our research activities in natural products is by exploring the different traditional medicines, specifically the therapeutic practices from several cultures, different cultures in the world, to find new inspiration in our research. As I say, to find new bioactive compounds or try to find new strategies to treat this infection, this bacterial infection caused by bacterial resistance strains. In this framework, we decide to study one traditional medicine as particular to find this inspiration. Is it the case of the Atacama people or Licanantai? They are indigenous culture in the north of Chile, and they live in very extreme conditions, like for example, very high altitude or great too high variation of temperature during the night and the day, and are in this condition that they preserve their culture, but also very important thing, they preserve and they continue to develop a very important medicinal traditional medicine that comes around more than 100 different medicinal plants, and all the ethnobotanic and all the ethnopharmacological use of these medicinal plants are well documented, but all the phytochemical point of view, all the phytochemical information of these plants, there were not rigorous studies at the time. So that's why we decided to focus to study the traditional medicine of Atacama people, because we thought that due to the extreme condition that they place, and due to the well-documented ethnobotanic information for the medicinal plants and the lack of phytochemical information, it was a great opportunity to, for one step, find new bioactive compounds, and maybe in a second step, find new kind of strategies to treat antibacterial infection. So with this spirit, we contact one community of the Licananti culture, specifically, the Charra community. It's a community, just one of several communities we can find in Chile for this culture too. And this is very important to mention, create and establish a collaborative project, an holistic collaborative project with this community and the laboratories, with different laboratories here in France, with the principal objective for one hand, for us to find new bioactive compounds, and for another hand, by the interest of the community, one to validate the traditional medicine, another one to valorize this knowledge by adding new information, new therapeutic information to this well-established traditional medicine. All this collaborative project started in 2015. And started with all the bureaucratic papers, administrative and juridic permission to establish this project. And also very important thing is in this project we made participate the entire community in each aspect, in each step of the scientific discussion, not only in collection of the plants or the collect of the botanic information, but contrary, we want to make them participate in all the step of chemistry and biological evaluation, because having their feedback that we will see in some specific case, having the feedback, the correct feedback from the entire community, help us also to develop and evolutionate the actual project to the state that is now. And without this feedback, I think we didn't have the opportunity to find the more precious and the more precious results and the more exciting perspective that we have today. So in this collaborative project, we wanted, how I said before, to the principal objective to find new bioactive compounds, but also to validate and valorize the traditional medicine of the community. So we planified different biological screening, but for the framework today, we will see the main results obtained in the antibacterial screening. Okay, but we also measure the antiparasitic, antioxidant, anti-inflammatory, and cytotoxic activities for all these plants. And we will see that they have antibacterial activity was the pole where we found the more promising results. So we started the project after all the administrative stuff that we made in 2015. We started with two field collection of the medicinal plants inside the community and supervised by the community. The entire community told us which kind of plants we were able to collect and how much able to take for the next step. In two different collections, always in September 2015 and 2016. From this field collection, we obtained a total of 18 species, 18 different medicinal plants, principally from the family of Asteraceae, but not even. We have also a lot of diversity, taxonomic diversity of these medicinal plants. But the more important point from this, all these collected plant, there were the lack of the phytochemical information, so we didn't know which kind of compounds we could find inside these plants. So then, after the collection, we continue with this is the common workflow in the natural product chemistry. We start the collection, then the extraction, and then we will screening the activity of the all extract. And then for the more promising, we will continue to characterize more deeply the biological activity, or in parallel, we can apply bio-guided fractionation in order to identify the bioactive compound responsible for the activity of the extract, and then start to continue to study, in this case, with the pure compound, but not with the extract, or in parallel. That will depend, obviously, of your project and of your objectives. For the extract, we base it that different plants are applied in the traditional practices by different methodology. Also, we decide to standardize this step of the extraction, and so we choose only two methodologies to prepare the extract: by pressurized solvent extraction and the supercritical fluid extraction for all the plants, all collected plants. And also for a few, for one collected plant, we decide to extract to perform one alkaloid specific extraction, because by chemotaxonomy we knew that maybe this plant we will find some alkaloids, so we apply this only for these plants, and a few distillation, because by the natural traditional practice, we knew that the plants are used as essential oils, not by maceration, decoction, or cataplasma, another kind of administration. So we also decide to perform this kind of extraction. And in total, after this step, we obtained more than 80 extracts that were taken and applied for all the screening that I mentioned before. But today we will only talk about the antibacterial activity, where we have the more promising results. As I said before, this activity was measured by one agar dilution method. Okay, so in this methodology, in one petri dish, we will mix the extract and with the agar in the petri dish, and then over the petri dish, after solidification and everything, we will put one drop of bacterial suspension, and then after incubation, we will see if at the concentration the extract was able to stop the bacterial growth. Okay, in this methodology, we will not see if the extract was able to kill the bacteria, or just to inhibit the growth of the bacteria. Okay, maybe the bacteria is not key, it's not dead, but the extract will be able to stop the growth, the bacterial growth. Okay, we will not see if the bactericid or bacteristatic. That's what I want to use. This screening was performed in two steps. The first step, with all the 80 extracts, were evaluated at only one concentration against different gram-positive and gram-negative bacteria, and then only with the active extract, the extract that showed an activity, were selected to the second step. The second step was the MIC evaluation. This is the minimal inhibitory concentration. So we will evaluate the extract at different concentration, only against the kind of strains, kind of bacteria that was effective in the first step. And then with the more active, sample, more active extract, we applied a bio-guided approach in order to elucidate, to identify the pure compounds, the bioactive compound responsible for the activity of the extract. So here we have the principal results. They are represented in a heat map. So in more more red, the less active extract, and the more green, that means more active extract with MIC values, the minimal inhibitory concentration, the lower value of this MIC. That means that we need less extract to inhibit the growth of the bacteria. In the first step, screening step, we didn't find any activity against gram-negative strains. So in the second step, we only use gram-positive bacteria. And for this evaluation, we found 2 extracts that were very active. That is a deserticula with MIC value from 10 to 60 microgram per milliliter, and then Krameria, the plant that we will talk more, the Krameria lappacea, with MIC values between 5 and 40 microgram per milliliter. Just to mention that, for example, the antibiotic of reference in this case was ofloxacin, presented MIC values between 1 and 3 microgram per milliliter. So in some cases, the extract, that is a complex mixture, presented very good results compared with the commercial antibiotic that is a pure compound. So with this result, we were very excited. So we move out with the bio-guided isolations. We fractionate. We will not enter into the details how we purify the compounds, but we follow several chromatographic steps in order to reduce the complexity of the extract and obtain more complex fractions. And then each fraction obtained after each chromatography step, they were evaluate the antibacterial activity, and then we can continue the fractionation, the chromatographic steps, only in the more active fraction in order to arrive only with the pure compounds at the end. Was in this case, after several chromatographic steps, we found neolignans from the active extract of Krameria lappacea. But the point, in this case, we found 5 neolignans, but only 3 in enough quantity. That is the big problem of the natural product chemistry. We didn't have enough quantity from all the compounds to be evaluated. So we could only evaluate 3 of them, and one of them, conocarpan, showed really good activity in the same model. Sorry, again, the same panel of bacteria with MIC value in this case for between 2 and 0.5 microgram per milliliter. That also some values very similar to commercial antibiotics. So, as I mentioned before, this was is a collaborative project with the entire community. So when with them we made some we have some scientific meeting with them, almost at least 1 per year. And when we found these results, well, we communicate this information, and then some more ethnobotanic information came to the light that in different reports they didn't have this information documented, that sometimes inside the community to heal or to treat some symptoms related to bacterial infection, they used to take also their traditional medicine, but sometimes in parallel with the modern medicine. That's mean, for example, if I have one respiratory infection, they will follow and apply the traditional medicine, but in parallel, they will also take modern antibiotics. So with this information, we try to see if there were any synergistic effect between these 2 medicines. We applied in our same model. We evaluate in our same model the medicine by itself and the combination. And here, as I say in the before when I explain the methodology, we can see here the a petri dish with the extract at a concentration of 12 micrograms per milliliters. And we can see here the bacterial spot. That means the bacterial growth after the incubation. So that means at this concentration, the extract were not able to stop the growth. And here we have also the same thing with gentamicin at 0.06 microgram per milliliter. Also the same kind of, we have a lot of different spots. That means the antibiotic at this concentration are not very effective. But at the same, in another petri dish, when we mix both the extract and the antibiotic as the same concentration described it before, here we can see the almost absence of bacterial growth. We were very excited with this because we are showing possible synergistic effect. But in science, we need to have some neat value in order to show this effect. So then we made another kind of experience. In this case was the evaluation of the fractional inhibitory concentration index in order to elucidate if two elements combined are more effective together or no effect, or they are better not together. That's what we call synergism, not interaction, and antagonism. Okay, and this fractional inhibitory concentration index is a fraction between the activity of each element in itself and the combination. And if this fraction is less than 0.5, for example, we can say if the synergism is 0.5 to 2, no interaction, and more than 2 is antagonism. We can see here from the KLAs is the active extract. We found some slight synergism, but when we evaluate also the conocarpine, the more active compounds, we found a very strong synergism between when it's in combination with the gentamicin, that is a reference antibiotic until today. So after this, this is the first step of the project. We were very excited because we could put some new information in on the table that about the antibacterial activity of this plant of Krameria lappacea. Just to mention, Krameria lappacea is already known plants because it's present in another kind of traditional medicines, but before, in the past, the plant was more studied in the framework of the polar extract, because we can make the extraction of other kind of compounds, and the non-polar extract of Krameria lappacea, they were not very good, very well studied. So this was one of the first serious report of this kind of extract for Krameria lappacea. We could also, for the first time, make some quantitative analysis of the antibacterial activity of this kind of compounds for this neolignans. In fact, they are not new, they are already known compounds, but they have they were more explored their anti-inflammatory activity, but the antibacterial activity, they were not very good studied. We could make that in a quantitative way to show the strong antibacterial activity of this kind of compounds, and also the synergies from in vitro of conocarpine with gentamicin. These were, as I say, very exciting results, but as I said before, our principal objective for us is arrive to maybe develop new antibacterial compounds to to find new kind of strategy to fight this antibacterial, this infection produced by antibacterial, produced by this bacteria resistant to the modern antibiotics. So this preliminary these results are very good, but we are kind of far away until to respond this objective until this point. So after this, we have we continue to explore to continue to analyze these plants and these compounds. But now it's at least we will discuss today about with 5 very specific questions about the role of tannins from these plants. We will see that, as I said before, Krameria lappacea was more studied the more polar extract. In this polar extract, the compounds that we can find they are tannins. We wanted to elucidate which kind of role they have the tannins in our model, if the tannins also present some activity in this agar dilution model, or really for the more active extract, the activity is borne by the neolignans and not by the tannins. Then we wanted also to characterize if these compounds or the extract is more bacteriostatic or bactericide action. We wanted also to know this. Then, if the compounds have also some effect on the biofilm, if the compounds or extracts are able to stop the formation of biofilm or to destruct the biofilm already formed. And also, in a chemistry point of view, we wanted to elucidate which kind of chemical function are involved in this activity, antibacterial activity, and then be sure about the no effect on gram-negative bacteria. And it's in this scope where the antivirulence that we will talk in the last part of the presentation were explores all these antivirulence activities. So to answer the first question about the role of tannin, this kind of compounds, we decide to perform a second collect. In this case, now with more quantity, where the data community was okay to perform this collect now in a more quantity of plants. In this case, and then we made a serial consecutive extraction, in this case by sample maceration, to elucidate then by chemical evaluation in which extract there are more neolignans, in which extract there are more tannins, and then try to correlate this information with antibacterial activity. So in this extraction, we made 4 extraction in dichloromethane, the more non-polar extract, ethyl acetate, and methanol. And the fourth one, the decoction, it was the traditional preparation of the plant. The chemical constitution for these 4 extracts was measured by molecular networking and the current replication strategies to elucidate in which extract there are more tannins. This chemical representation, chemical evaluation was made by HPLC PDA based on the mass fragmentation spectra for each compound. So in this case, we will compare the experimental MSMS fragmentation spectra of each compound or for extract with existing literature or with database that are open online to see which kind of compounds we can find in each extract and what kind of family of compounds they are present in each extract. So in this case, we observed more a percentage more elevated in the percentage of neolignans, about especially the type of hydrogen benzofuran and benzofuran in the more non-polar, in the less polar extract. Sorry, that means in the extract of dicloromethan is where we found the more quantity of neolignans present, and then also by this methodology and by direct quantification of tannins, we also found that the M1, that is the chloromethane extract, we found the less quantity of tannins. The tannins were more present in M3, that is, it was the methanolic extract, and in the decoction is where also we found the less quantity of neolignans. And then when we verified the antibacterial activity of this extract, we also found it was M1 the more active extract for far away by comparison with the rest of extract. So in this case, we could answer the first question that the role of the principal role for the antibacterial activity of non-polar extract from Krameria lappacea is by the presence of neolignan and not from tannins. Then for the antibiofilm activity of the extract, we also perform another kind of experiments in order to, for one side, see if the extract were able to stop the formation of biofilm, and second, to destroy if they were able to destroy the biofilm. We have to remember if in one cytose infection, pulmonary of another infection in the body, the bacteria, they are not planktonic bacteria. They are not just one bacteria alone. The bacteria, when they make the infection site, they produce, like we say, the biofilm. That is a complex matrix where the bacteria live and multiply. And to access to this biofilm is very difficult for some antibiotics, because the antibiotic must to pass through all this construction that is very complex with different kind of compounds, extra compounds. So to access to the active site for the antibiotics, sometimes they're very difficult, and then we need to go through all this antibiofilm in order to arrive to the bacteria. So we wanted to know if the extra were able to destroy or to stop the formation, and we found that the extract were more able to stop the formation than destroy the biofilm. In fact, the extract were not able to destroy the biofilm in gram-positive or gram-negative bacteria, but more they were able more than to stop the deformation, the new formation of new biofilm. That was the second question, and the third question was to know which kind of chemical fusion in the structure of this kind of compounds were involved in the antibacterial activity. So in this case, we also performed the de fractionation in order to corroborate our findings on the first step. We could isolate the same compounds, the same 5 compounds obtained in the first time, but also now we focused it also in the fraction where we knew that maybe there were some another neolignans, even if they were not active. We wanted also to purify it and to isolate them, because they were very informative to us to see, okay, this kind of function that now is present maybe is not very good for the activity, and having this kind of results. So we performed an exhaustive second purification of lignan, of a neolignan. In this case, we could isolate 10 neolignan in quantity enough to all the purification, and also to perform a structural modification for the active compounds. In this case, we applied also another kind of models. If one when we in another kind of all kind of project, if you want to valorize and say this compound is active for each target or for each in each model, it's better to have the activity in the more different models possible, in order to see if your compounds is model specificity, or you can also show the compounds also exert the activity in different conditions and everything. This kind of information are very, very important for the development of the compounds, if you want to go to the therapeutic field, for example. So in this case, we also made the agar dilution that I described before, but also the broad microdilution method. That is the methodology that I think you must to know about in liquid media. And here we found that the compounds 2, 3, and 4, they were the more active. The conocarpan that we saw before, the more active, it wasn't the more active in this model. So this kind of also interesting result for us. And then also another agar diffusion method. And in this case, we found the activity, the more active activity was conocarpan, but maybe because this compound were more able to diffuse in the agar than the other compounds that were more active in liquid media. And also we found another one very active, C4, but it was isolated in the first step, but with not enough quantity to be studied. So now we have the more quantity. We studied the compound, and we found in several in two models they were very active, even sometimes more than conocarpan. So we found that C1, C2, and C3, and C4 were the more active, and which kind of feature that we have here in this case was the point about the double bond here, and always the phenol group in the position 4. After then, we have this compounds in enough quantity in order to perform some chemical modification in the structure. We perform the methoxylation and the acetylation in this position, on the phenol position, in order to see if there were some effect on the presence or the absence of this proton donor. And then also the reduction of the double bond to know if the electron density and the rigidity from this compound, or from this in the theoretical target site, there were any influence of the presence of these elements in the antibacterial activity. We performed the structural modification, no problem. They were not very difficult procedure to perform. But when then we performed the antibacterial evaluation, we found total absence of the antibacterial activity in vitro. So with this kind of result, for this kind of compounds very specifically, the present, the antibacterial activity must to exert antibacterial activity from these compounds, having the double bond and having the phenol in position 4 free, are very important to exert antibacterial activity. Maybe there are other compounds that we don't have that, and we still have the antibacterial activity. But for this compound, conocarpan, and for CCAT, that's what we are working right now. We can say this very affirmative that for this compound, having this both feature in the structure are kind of essential to exert antibacterial activity. And then for the last part, we wanted to know if this compound had any effect on gram-negative bacteria. Why? Because for some acute and more chronic aggressive infection, they are the gram-negative bacteria that we found more present. kind of the gram-positive bacteria, sometimes they are more easy to kill or stop the growth. So the more difficult bacteria into now to work, they are the gram-negative bacteria, because for the double membrane they are more difficult to stop or to treat the infection. And for try to have a new kind of therapeutic option to treat this kind of infection, there are some laboratories that started to focus not directly to kill the bacteria, to kill the biofilm, for example, and go and to kill the bacteria, but they were more focused, and we will. This is very important I think for the next generation antibiotics, is to try to transform the pathogen, the gram-negative bacteria that is very pathogen, less pathogen, in order to be treated with less aggressive antibiotics. And how we can do that is attacking the virulence factor that they are known by the bacteria, by the pathogen, that there are strategies, there are some mechanisms that the bacteria possess and exert in order to express the pathogenicity, or to exert another kind of strategy to be more virulent, more pathogen, more easy to make infection. Each bacteria has their own virulence factor. That's why it's kind of a strategy that they start to be developed, but how is very specific for each bacteria. The scientific, the more biological laboratory, they take more time in order to identify, understand one virulence factor, and then try to take down or to supprime this virulence factor, and what could this be in the infection site, for example. So this is this approach that is more complex, that will take more time to be put in place. But for example, for Pseudomonas aeruginosa, that is a gram-negative pathogen that we found in some very aggressive acute and chronic infection. There are some virulence factors that were already known, studied in the literature. So we started with this bacteria, and we focused on the virulence factor produced by Pseudomonas aeruginosa to exert the cytotoxic activity of this pathogen. In fact, in the we will by the Pseudomonas aeruginosa, this pathogen will secrete some cytotoxic compounds that, what in the infection site, they will kill the human cells, and then the pathogen can, for one site, feed itself with the cell death, and then liberate the place and continue this pathogen has this bacteria can produce this kind of toxin, cytotoxic bacteria, but we focus in one specifically that is already a cytotoxic compound that is a green pigment, cytotoxic effect on human cells, and also diffusion visible in the membrane fluidity that we will discuss later. We wanted to know if our compounds were able to affect the production of. So, as the biosamin is a green pigment, we can follow the production by, and we found that in the presence of chlorcarpan, the were able to produce less less of this cytotoxic compound. In a dose-dependent way, so we were very happy to report this because for these compounds, this kind of antivirulence activity were unknown until this time. And then, as I say, for this pyrosaline, it is also involved in membrane fluidity. So we want to know if this kind of this compound, chronocarpan, also have an effect in the fluidity, in the rigidity of the membrane bacteria. And we found also in this case by fluorescence, by the use of fluorescent probe, where the more fluorescence we have in the presence of chronocarpan and with this probe, that means that the membrane is less rigidity. Sometimes means it's more permeability because there are more probe that can go into the membrane and then extract the fluorescence. And we saw that this compound is able to shape the permeability of the membrane, and this is very interesting result because in this case we can also imagine the antivirulence evaluation on Pseudomonas aeruginosa of with, for example, one antibiotic that is already where the Pseudomonas aeruginosa already present resistance to this antibiotic. For the antibiotic we can evaluate by, for example, disturbing the entrance of this antibiotic to the bacterial cells. If we make a synthesis, for example, evaluation with this compound, maybe we will contrast the bacterial the antibiotic resistant of Pseudomonas aeruginosa, and in this case, we can be able to answer our first objective to find maybe new strategy to contrast this and to treat this kind of infection produced by multi-resistant bacteria. So this is the actual state of our research right now. We already answered our 5 main questions that we talked about before. But when you have good results or interesting results, you will always have more questions to answer than if there are negative results, because now we have to think about the potential optimization of the structure. Now that we know that the proton donor must be free and the double bond must be present, we open now new questions because now with these elements we were able to optimize the activities done compound, and then a second step that is the record of the activity, but now in vivo models, now out of in vitro models, but now we have to attack the different in vivo models, try to establish some synergies evaluation with resistant bacteria, specifically the Pseudomonas aeruginosa resistant strains, in order to, thanks or based to this effect of chronocarpan to make more membrane, we could cause some resistance have developed this kind of pathogens. So this is the future answer that we now try to, the main 3 questions that we will try to answer in the next years. So we'd like to thank again for the invitation and the attention that you give me. I will be more happy to answer any question that you have.
Thank you, Professor Sergio. Well, se alguém tiver alguma pergunta, comentário, questão, pode fazer aqui no chat que eu faço a transmissão em inglês para o professor Sergio. We have some delay between what we are talking here and what they are listening in the YouTube, so sometimes there are a few minutes that we need to wait.
They will arrive. Yes. Okay.
But I have some doubt, some curiosity, that is if... Opa! Eu acho que ele caiu. Aparece 20/6, mas não tem problema. A data está certa. Já corrigi aqui, mas não sei se aparece, se vai corrigir no formulário de vocês, mas não tem problema aparecer 20/6. Eu já arrumei. Acho...
Hello? Is it okay now?
Yes.
Yes.
Yes. I think your internet...
Yeah. Sorry, I don't know what happened, but I will try not to touch anything now.
No problem. I have a curiosity that if... Did you know the safety of these compounds, the cytotoxicity in mammalian cells?
They're not toxic. No. Well, no, I didn't mention that, but the cytotoxic activity for all the extras were also evaluated. So no cytotoxic on human cells were recorded for the extract in the different steps. And also the fractionation, the bioguided fractionation, we also evaluate the cytotoxic activity of the fraction. So we continue only with the fraction that they are active but not toxic. And then reevaluate the cytotoxic activity in a panel of human cells, cancerogen and not cancerogen cell lines. We didn't find any effect at the same concentration that we record the antibacterial activity. They have some cytotoxic effect, but at 100 or 1,000 factor more concentrate than antibacterial activity. So if we wanted to continue to explore the antibacterial activity of this compound, we will more than safe at this kind of concentration. Yes.
The antibacterial concentrations are much less than the toxic concentrations. Great.
Yeah. For this, for the more active compounds, we are already in the micro nanomolar range, and for the cytotoxic, we are in the millimolar molarity. So maybe we will have to, because with the spirit to have new antibiotics, that is. For now, it's not the spirit of the project, because if we take out one, we can develop one antibiotic for sure. In a few years, we will have resistance. We are more attacking the side of the probably adjuvant administration. That means one antibiotic with this kind of compound. How this treatment are also considered to be long as 1 week and everything, we have to be focused to see any cytotoxic toxic effect in this period of time. For example, in some in vivo models, to be sure that we are safe at this concentration.
Great. I think we don't have any more questions here. So thank you for the webinar. It was very interesting results.
Oh, thank you.
I will end the transmission. So, obrigado, pessoal. Nos vemos novamente na próxima semana. End the transmission